Alright. Put your hand up if you're ready to train food vision big. You might have already given this a shot, but let's do it together. So this is going to be the biggest model we've trained so far. So things for training, what do we want to do? Well, we'll keep experiments short. We'll go 5 epochs to begin with. We can always increase this if we find good results. The next one is going to be our optimizer, which is going to be torch.optim.atom with LR equals 1E negative 3. And then our loss function, here's a little trick I'm going to introduce here as well. So you might have already used this loss function, torch cross entropy loss, but I'm going to introduce the technique of label smoothing. And label smoothing is a very powerful regularization technique that comes basically for free. So that means we can just implement it like that, and it's going to help prevent our model from overfitting. Now, of course, where could we find out what is label smoothing? What is label smoothing? To smooth or not? What is label smoothing? Okay, we've got a good resource there, or potentially good resource. Papers with Code always has great explanations of things. Label smoothing is a regularization technique. Regularization is what? Prevention of overfitting that introduces noises for the labels. This accounts for the fact that datasets may have mistakes in them, so maximizing the likely of log probability y given x directly can be harmful. So there's some more information there, but if we go into another resource, so this is from Yushong Wong. What is label smoothing? A technique to make your model less overconfident. So if we go down, I like this part at the end here. When do we use label smoothing? Whenever a classification neural network suffers from overfitting and or overconfidence, we can try label smoothing. So right now, we don't know whether our model is going to overfit or not. But because this is a machine learning cooking show, I have already tried to fit a model without label smoothing. And I can tell you that using label smoothing helps because we have so many classes. We have 101. And you might be thinking, well, Daniel, where do you get these things from? Well, we've seen, if we go to PyTorch state of the art, we've seen this one already, state of the art training, the blog post. So this is where machine learning is part cooking, part science, is that a lot of the time it's by experimenting and trying different things. So here's label smoothing. I chose to use label smoothing out of all of these because like trivial augment, it's one of the easiest to implement. We can get away with it by going torch and then cross entropy loss with a single parameter. Label smoothing equals something. And torch, what did they use? The torch vision team. If we look for label smoothing, what was the value they used? There we go. Label smoothing equals 0.1. We use PyTorch's newly introduced cross entropy loss label smoothing parameter, and that increases our accuracy by an additional 0.13 or 318 points. Now, of course, that's on ImageNet. So let's give it a shot trying it out for our own problem. We'll come back here. Label smoothing. So first and foremost, what do we need to do? Or actually, let me give you another little overview of what it will do. So why use label smoothing? This is another bit of intuition. So label smoothing helps to prevent overfitting. It's a regularization technique. So if you were to go and further research it, you would probably find something without label smoothing and 5 classes. I'm only using 5 as a demonstration purpose, but this will go for any arbitrary number of classes. Your model output might be something like, or prediction probabilities after we've gone through softmax, might be something like this, 0.99. So it's very confident on the middle class and basically assigning nothing to the other classes. So what can happen sometimes with neural networks is because they're so powerful, they become overconfident on one particular class. So what label smoothing tries to do is it does this. With label smoothing and 5 classes, the output of your softmax layer might be something like this: 0.01, 0.01, 0.96, 0.01, 0.01. You see what it's done here? It's smoothed out the overconfidence. So it's taken from here and assigned some values to the other labels. So this helps to prevent overfitting. Again, it's not guaranteed, but it's one technique to try to do. Helps overfitting to stop the model from getting too confident on a single class and at least assigning some prediction probability, or at least considering another class as an option. So that's the crux of label smoothing. But of course, if you want to do your own research and learn a bit more, you're more than welcome to do that. Let's see it in action. So from going modular, let's train the biggest model we've trained so far. Going modular, import engine, and then we're going to set up the optimizer. Optimizer equals torch.optim.atom. Params equals fnet b2. We want to optimize the food 101 parameters, of course. And then our learning rate is going to be 1 e -3. And then we're going to set up the loss. This is where we're going to introduce that new label smoothing parameter, which is generally helpful for when you have a large number of classes. Torch.nn cross entropy loss, and we can just implement it just like that. Label smoothing equals 0.1, and then let's go. Our goal is we want to beat the original Food 101 paper's result of 54 or 56.4% accuracy on the test data set with 20% of the data. And if you're paying close attention, you might notice that the Food 101 paper achieved this result on 100% of the test data. So truly, we're not really comparing our model as apples to apples when we train on and evaluate on 20% of the Food 101 data. But we're going to see how it goes. And then, of course, later on, you can train this model on the whole Food 101 data if it goes well. If it goes well, that is. No spoilers. So we're passing in our train data loader here, Food 101 20%. Then we can do the same with the test data loader, equals test data loader, Food 101 20%. And why is that telling me I've got an error? Is there a typo there? Colab, you couldn't keep up with my fast typing. The optimizer equals optimizer. Our loss function equals our loss function. Epochs equals 5. And device equals device. Now, once we run this, it may be running for a while. So I just want to highlight the fact of what GPU I have access to. Now, this should run on almost any GPU, but I have quite a, because I'm using the paid version of Google Colab, I have quite a good GPU here in the Tesla P100. So if you're using the free version, this should still work. It just may take longer to train. If you're running this locally as well, depending on the hardware you have, will depend on how long this model takes to train. Because after all, we are training on 20,000 plus images. So you ready to go? We're going to bring Food Vision big. We're going to train our biggest model yet. In 3, 2, 1, let's go. Oh no. Here we go. So we're not going to know how long it's going to take for a while until it's finished one epoch. But the good news is we've got no errors so far, so it's going through the train step function, get data, try get data, etc., etc. Train step, beautiful. So it's training, wonderful. It looks like our model is working behind the scenes. Now, while we wait for our first epoch to finish, how about we start preparing some of the next sections? So of course, we want to inspect the loss curves of our Food Vision big model. And how do we do that? Well, we can go from helper functions, just like we've done before, import plot loss curves, and then we can go plot loss curves. So we'll get all this ready ahead of time, hey? Food 101 results. Just while we're waiting for the first epoch to come up, then we'll have a little bit of an idea how long this model will take to train. Then let's get the next one ready. What will we want to do? Well, if our model is performing well, we want to save and load food vision big model. And we've done this before, so I'm going to let this keep training here. But let's write some code to get ready. So from going modular, we're adhering to our PyTorch workflow here. So create a model path. Potentially we call this one FNet B2 Food 101 model path equals 09 pre-trained FNet B2 feature extractor and Food 101 20%. Remember, our goal here is to try and beat the original Food 101 paper with 20% of the training data. And we're going to save the Food Vision big model with utils.save model, and the model is going to be FNet B2 Food 101. Of course, this is our model up here. Once it's finished training, we're just preparing this code for when we know how long this first epoch is going to take. It should let us know how long subsequent epochs are going to take. The target directory will be models, and then we'll put the model name is going to be FNet B2 Food 101 model path. Wonderful. And then what do we want to do after that? Well, let's load it back in and see how it works after we've saved it, of course. So we'll create a Food 101 compatible FNet B2 instance, and then we'll go loaded FNet B2 Food 101, and this is where our function that we created before, FNet B2 transforms, create FNet B2 model, num classes equals 101. So we're just creating an instance of it there, and then we can load the saved models state dictionary, which is what we're saving with this function up here. So loaded FNet B2 Food 101, we'll go load state dict equals torch.load, and then we'll pass in the full file path here, which will be models / this one here. And we'll just get rid of those extra apostrophes. Beautiful. So that's going to be saving and loading the model and plotting the loss curves. Oh, we're so ahead of time here. But it looks like our model might be doing a test step. Beautiful. So we're almost finished through the first epoch, because the way our train function is set up is that it goes through all of the training data loader first, and then it evaluates. So what can we do after this? While we're waiting for this first epoch to finish. You're getting experience here as a real machine learning engineer, right? Because a lot of the time you're trying to work out things to do while your model trains. So we'll check out Food Vision Big model size, but we'll save that for a second because I think, oh, there we go. Look at that. Oh my goodness, the first epoch of Food Vision Big. Have a go. Epoch number 1. The training accuracy is just under 30%, but recall this accuracy value, or these accuracy values, are across 101 classes. And then, oh my gosh, we're almost at 50% accuracy already for the first epoch. So what's our goal? 56.4% accuracy. Okay, we've got 4 more epochs to reach that. But it looks like on my end, on my P100 GPU, it's taking 264 seconds per epoch. So what is that? 264 divided by 60, what do we get? Oh, well, that's not going to work, is it? 264 divided by 60. So about 4.5, 5 minutes, give or take, per epoch. So that means this is going to take, I'm going to write a little note here. So note, depending on your hardware, running the following cell may take 15 to 20 minutes. Takes about 15 minutes, or maybe longer. If it's 5 minutes per epoch, it might take 25 minutes, or 4 minutes per epoch, or 7. It's saying it's going to take 17 minutes total, so I'm going to say 15 minutes. Takes about 17 minutes on a NVIDIA Tesla P100 GPU. So again, depending on where you're running this may take a while, but As I said before, one of the big problems in machine learning is figuring out something to do while your model trains. So I'm going to go take a little walk and stretch outside for a bit, maybe make a cup of coffee, and I'll come back once training has finished. If any errors happen, I will let you know, but I'll see you once all of these epochs have been completed. And I'm back. Look at that. Training is all done. We've got a green bar, and check out that. The test accuracy, we've trained our biggest model yet, Food Vision Big, is just under 58% accuracy, which, look what we've done. We've beaten the original Food 101 paper's result of 56.4% accuracy with only 20% of the data. So that is very exciting. Why is that? Because we've just done something on my end, it took about 18 minutes. 18 minutes for training, may have taken a bit longer depending on the hardware you're using, or if your hardware is faster, that might have gone quicker. In 18 minutes, that wasn't possible 10 years ago. With free hardware and, well, I'm paying for Google Colab Pro, but it's quite cheap compared to, you get the picture. And free software. Have a look at this. When did this paper come out? Maybe in 2011? Food 101 paper. Do we have a release date up the top here? Doesn't look like we do. Let's have a look. When did the Food 101 paper come out? 2022. 2014. So just under 10 years ago, because it's 2022 as I'm recording this. But if we look in here, days, look at this. This is paid by a considerably longer training time of 6 days. So the original paper took 6 days to train on a NVIDIA Tesla K20X, whereas ours took just under 20 minutes. How cool is that? That just shows how far the field of deep learning has come. Now, like all good cooking shows, we've prepared this earlier. We've written this code before to inspect our model's loss curves. Let's check it out. Oh my goodness, they are some good looking loss curves. Even with all the extra data and extra classes, our model is still performing well. And you know what? If we kept training for longer, I think it would even improve. Those data regularization techniques that we use and model regularization, such as label smoothing and trivial augment, data augmentation, look like they're helping because our test loss is still lower than the training loss, which means our model still has more to learn or is hinting at that. Now, of course, we can save the model and load it to verify that it works. Beautiful, saved and loaded. And while our model was training, I went for a little walk, made a cup of coffee, and also wrote this code here to check the Food Vision Big model size, which is what we've done before, except with just a different path here. So let's see what the model size is. Wonderful, it's only 30 megabytes. So why is that? We've trained it with a lot more classes, but really all we've done is compared to EfficientNet B2 for Food Vision Mini, oh my goodness, we've covered a lot of ground, which was only 29.8 megabytes, we've only had a slight increase in model size. The reason is because we've only increased the number of parameters in the final layer. We've kept all of the base parameters the same. So if we get a summary of our model, let's get our FNet B2 summary, and we'll get this as well. We'll go right down to the bottom. There we go. This is for FNet B2, not FNet B2 Food 101, so that's going to be for Food Vision Mini. So we have a total parameters of 7.7 million, thereabouts. And then we can go here. This is for FNet B2 Food 101. So if we look at the total number of parameters, we don't have that large of a discrepancy here, about 100,000 more or so. So that is only changing our model size slightly. So we should get all the benefits that we've got with fast inference time for our original Food Vision model, Food Vision Mini model that is, for our Food Vision Big model. So with that being said, we've got our biggest model yet, Food Vision Big. I think let's deploy this into an app, eh? Let's replicate Food Vision Mini, our deployed app, but with our Food Vision Big model. So you might want to go ahead and give that a shot. We've already done all the steps that we need to do up here, deploying our Food Vision Mini app to Hugging Face Spaces. and creating a Gradio app with it. So my tip to you would be to first create a Gradio app that works within Google Colab using Food Vision Big, and then try and deploy that app to Hugging Face Spaces. And that's what we're going to work towards in the next series of videos. I'll see you there.